Computing low energy excitations in strongly correlated systems.
Okay, so today I'm going to talk about something which is not very common in a multi community, is a bit of solid states. And here we are trying to look at excitation, magnetic excitation in solid state, and which are the low energy excitation in strongly correlated materials. No, in the
Just
Try again.
Okay, thank you. So in strongly correlated materials, you have this is the here I plotted the density of states across the multibar transition. So when you have a metal, is this one? Okay, no. I'm sorry, that doesn't work. No, I don't. Okay, so I thought it was the one.
No.
Okay, I'm sorry.
No worries.
Okay, so here you have the classical Fermi liquid, and when you are very strongly correlated electrons at the Fermi level, and you cross from the metal to insulator transition, you go through some shape of the density of state, which is like this, where you have an effective Fermi bond, which is much reduced, and where the excitation does not correspond to quasi-particles, which are the single excitations in the quantum chemistry language, but rather to collective excitation, like density wave, etc. And when you come to the insulating states, then the low energy excitation are magnetic excitations. And this is why we are interested in this kind of excitation, to look at this kind of problems in physics. We can do that with multi-cycle methods by using embedded fragments. And for that, I can go to the specific code that has been recently developed that helps to design an embedded fragment for magnetic excitation. And since it's strongly correlated, you need to have highly MRCI methods and a fully decontracted method because of the strong correlation. So here I'm going to discuss a bit what is the physics behind the magnetic excitation. Here I've taken 1 electron per site. You know it's a singlet triplet excitation, but what is the physics in there? You have 3 types of, if you do a QDPT analysis, you have 3 types of contributions. One is the direct contribution of the exchange of 2 electrons between the magnetic orbitals. The second thing is to have a hopping of 1 electron one side to the other, and then back the other electron. And the third term that appears when you have a ligand between your magnetic atoms is to first take a ligand electron, move it on the magnetic, on the metal, then take from the other metal the reverse spin electron and put it on the ligand, which brings you to 2 intermediate states, and do the reverse spin. Okay, all those terms that you see here are the main physics. The main term that contributes to the magnetic excitation and that we have to treat properly. But this was for 1 orbital per site. When you have many orbital per site, of course, you have all kind of contribution on the same one, which are similar. Another thing is that when you have many open shells per atom, you may not want to have all the classes here, because, of course, then putting all the spins on one side and not on the others have no sense. So you may want to select within the classes here atoms which are high on each side. Okay, so what do you need? If I go by this analysis, you need a multi-configurational method, you need an equal treatment of the ground and the side space. So you need to have all the configuration that are building the magnetic excitations for all the open shells orbitals included at the 0th order. And then you need what is called spinning effect, which we call dynamical polarization correlation, and which means that we need all the single excitation on the references that participate to the magnetic exchange problem that I showed. Okay, and we need that to have it in a fully decontracted scheme, because in this kind of systems, the dynamical correlation changes the relative weights of the different contributions, the different determinant that you have in your reference space compared to what you can have in class. Okay, so one thing that whatever we do not need is all the spinning effects which are common to all the states we are interested in. Okay, so for that we develop a method which takes an equal footing the magnetic and bridging orbitals, where we make a selection within the classes. In order to, where here we could say, okay, how do we define orbital? We can make the classes here on the magnetic orbitals, but as I tell you, when the number of magnetic orbitals per atom increases exponentially, it increases the size of the class increases exponentially, and when you will put all the dynamical correlation effects, then it will explode the CI that you want to make. And so you make selection, and so you will define a method to get your magnetic excitation accurately. In this way, you will here have your dominant configuration on each magnetic atom. You will put the charge transfer, which are the excitation from the ligand to the metal, and the metal to the ligand if you whichever orbitals which are bridging are virtual orbitals. And then you will have to put all the spinning effects. And you have to ensure that you have to put a bit more, because if you want to have eigenfunction of S square, you have in fact a few more configuration in order to ensure this. And so we have built a code which is interfaced with MoFast and also MoFast to do this kind of calculations, where you provide the magnetic orbitals, the set of orbitals which are coming from a SSCF calculation. You localize the active, you equalize the active orbital, which are the magnetic orbital on each atom. From this, you identify the bridging orbitals which bridge the interaction within the occupied orbitals of the classes here, or the virtual, if they are virtual bridging orbitals. And you do the integral transformation. And then the code can do this fast that method, which is I have described above, but some other ones, and have a different, so an increased number of classes orbital with those ligand orbital either occupied or virtual, where you can make those excitations from those charge transfer excitations from the ligand to the metal, or the metal to the ligand virtual orbitals, which are taken as reference. If you do that, our code is fully parallelized. It is interfaced with MoFast and with an open license, and you can go diagonalization up to building determinants. So just to give you a few information on how it scales, this is the scaling with the number of determinants, which is pretty linear. And this is the scaling with the number of MPI processes, and the scaling with the number of OpenMP processes, because it's a code which is fully parallelized both with OpenMP and MPI. And just to give you a few ideas of the kind of accuracy that we can get, here I have taken systems which is nickel fluoride, which is a perovskite. And so here you may have a quantum fragment which is embedded. Here this is the experimental value, which is 7.7 that you get from inelastic electron scattering. And then this is what we get with our methods. So you see that what we are trying to reach is the MeV accuracy from excitations. If I go to another system, for instance, here I've taken cobalt, where now we have 3 open shells per atom. And again, I get a very good accuracy at the million. Here I took manganese, where here I have 4 shells per atom. And again, this is experimental value. This is the experimental value, which I take from an elastic electron scattering. And here, this is the value for the 2 types of integrals that we have. So as you can see, by putting having a thorough analysis of what is the current contribution to the magnetic excitation, and doing CI, where I put all those contributions as a reference and put the dynamical polarization on it, on each of the configuration, I can get very, very good accuracy on magnetic excitations. And I thank you for your attention. The call is fully available there.